So yeah, I'll do a quick intro for folks. I don't know how many folks have been here the previous weeks, but anyway, welcome folks. We do this every week. It says YFTT, Yugabyte Friday Tech Talks. It's an event for engineers by engineers, and we mostly discuss the ins and outs of a particular feature, right? And we do that every week, same time, same place over Zoom. Anyways, this week's talk is about, hey, Kurt, good morning. Thanks for joining us. Been a couple of weeks since I got on, but good to see you're here. Awesome, and you can always trust Kurt to ask very interesting questions. So other folks, yeah, drop by, in the LinkedIn comments, just say, feel free to say hi or just ask questions anytime you want. You guys can also feel free to join our community Slack, yugabyte.com/Slack, and go to the YFTT channel if you want to continue asking questions. Okay, so with that, quick intro about Rob. Rob was one of the engineers that worked on this feature. This is an insanely complicated area in general, like, concurrency control and isolation levels and all of this stuff tends to be pretty hairy, pretty tricky, and databases like Postgres are actually pretty advanced. So I'm really happy Rob's doing it. But do you want to give maybe a minute intro, Rob, and we can get right into it?
Yeah, so I'll just, thanks for the intro, Karthik. I'll just jump right into sort of what, I'll introduce the topic. If you're not familiar, there are sort of two concurrency control or locking schemes that people like to talk about. One is optimistic locking, another is pessimistic locking. And when we talk about these two alternatives, we're looking at how do we deal with transactions which are in conflict with each other. And in the optimistic locking case, the strategy is to essentially, upon the detection of a conflict, have some consistent way to decide which of the transactions involved in that conflict we want to roll back.
Yeah.
So upon conflict detection, it's that's sort of it for at least one of the transactions. Whereas in pessimistic locking, we have a strategy whereby a conflict is detected by some transaction and it will wait. Essentially wait its turn to interact with a key that is being interacted with by another transaction. So yeah, okay. I can pause there.
Why do we need it? I mean, maybe give a 1 minute motivation on why pessimistic locking. Most of the viewers should know it already, but it's still interesting to answer the question, right?
Yeah, definitely. So as I said in describing optimistic locking, essentially our strategy is to abort one of the transactions that has found itself in conflict, and that requires us to kill transactions which can harm your workload. If you have a highly contentious workload, suddenly you are causing transactions to roll back when maybe they didn't need to. Whereas with pessimistic locking, you are giving these transactions a chance to resolve. It's especially useful in read committed isolation level, where the introduction of pessimistic locking essentially allows all of your conflicts to be resolvable by waiting. With snapshot and serializable isolation, there are some cases where a transaction will wait and still has to be rolled back after waiting. But in all cases, we expect contentious workloads to perform better with pessimistic locking.
Got it. That's awesome. So I heard two things. One is performance for contentious workloads. Like typically you think of optimistic locking as being better performing, but only if the workload is not contentious, right? And if it is, then pessimistic is better because you don't have to keep repeating the work. And the second thing I heard was, make it, simple to build an application. Don't have to deal with all the various forms of restarts, et cetera, et cetera. Those are the two, right? Like predominantly.
Yeah, exactly. I mean, with optimistic locking, you'd have to handle restarting your transaction and ensure that your clients are kind of well behaving in that case.
Got it. Awesome. All right. So let's go into maybe a real difference between pessimistic and optimistic locking, and we go from there.
Yeah. So let me share a different window. I want to kind of demonstrate a case where optimistic locking fails and pessimistic locking succeeds, does much better. Let's see. Need to find the screen here. Okay. Can you see this?
Yes, I can.
Okay, great. So this is two YSQL sessions connected to a cluster where optimistic locking is active. So let's see. We have this, this table. It's just a very simple kind of bank account like table.
Okay.
And suppose in one of our sessions, so let's demonstrate with the snapshot isolation. So in one of our sessions, we want to read from these two accounts and transfer some money. So this is sort of the case where Bob is sending Alice all of their money for whatever reason.
Yep.
And so we select both of these rows and we kind of grab explicit locks saying, hey, we're gonna read these to update them later.
Okay.
Now in a separate session, let's actually do these updates first. I'm just copying from off screen to save time.
Yeah, no, totally makes sense. Yeah, I was just thinking you were just like a wizard with typing, but that's okay.
Oh, yeah, sorry. I realized that might be confusing.
No worries.
Okay, so yeah, in this session, we have this transaction open where we've read from Alice and Bob, and we've transferred all of Bob's money to Alice. And so, you know, in your application code, it probably wouldn't, you know, this 150,000 number would be generated by adding these two numbers up, and you know.
Yep.
So in the second session, now we want to, hold on. I copied the wrong thing. Let's say we want to read from this row. Oh, you know what? This is the cluster with pessimistic locking. So we
are seeing pessimistic locking. Yeah, we're seeing
exactly
pessimistic locking. Yeah, let's complete that. Maybe then we go to the optimistic locking. That's fine. Yeah.
Yep. Actually, sorry, this is a little bit unexpected, but demos seem to never go quite as planned. But
of course, that's fine.
Yep. So essentially, in this case, what we would expect is when this select happens, one or two of these transactions would fail. In this case, the transaction on the right is failing, and you know we can commit this one, but at the expense of this one on the right.
That is optimistic behavior, right? That is optimistic behavior where one of the contending transactions will succeed and the others will fail, right?
Correct. Yes. So let me just double check that this was, apologies.
No problem.
Yeah, so that was the optimistic behavior.
So that was the right thing. Yeah. Okay. Got it.
Yes.
Yeah.
Yes.
Okay. No
yep.
worries.
Okay. Cool. So let's switch to pessimistic now.
Okay. So you've got all these windows pre-canned. I think I could see the source of your confusion.
Yeah. Yeah. Exactly. Too many windows. Yeah, the preparation leads to more confusion sometimes. And yeah, let's just confirm. We have the same situation here. And we're going to essentially do the same thing.
Same thing, yeah.
And in this session, right, so in the second session, when we try to select the balance analysis account, we see we block, whereas in optimistic blocking, one of these transactions would be rolled back.
Yep.
Here we can commit on the left side, and in so doing, we release the right side, and we'll note that we got the right result here, 150,000, and not that. We select this should work as expected as well.
Got it. Yep.
Yeah, so that was a bit of a rocky but hopefully useful demo of
that makes total sense. Yeah. And so I think this gets even worse if there are, say, 20 threads trying to do the same thing. And in optimistic, you'll have to keep building the retries on the 20 threads. And just putting the hat of a application programmer on, if it was optimistic locking, then they'd have to do a back off and retry with some timeout on the app side. And they'd have to do it at least 20 times, right, to guarantee success, because there are 20 other threads, except you don't know how many times because you don't know the concurrency, and that's what makes it really hard, right? Whereas here, you just let the database deal with it.
Yep, perfect.
Got it. That makes sense. Cool. So, yeah, what else were you going to tell us? Because I have a bunch of questions on how things work. Like, how does this whole thing work? Like, this is a distributed database, so that means it runs on multiple different nodes. And so when you say start something for pessimistic locking, I am curious about how it really, does this
Yeah.
thing? Yeah.
So with the benefit of pessimistic locking, waiting and potentially avoiding conflicts, we have this additional problem where you might have multiple transactions waiting and causing essentially a deadlock, right? So in optimistic locking, this is avoided because anytime a conflict is encountered, it's resolved. And so,
but even before deadlock, right? Maybe let's even do the simple case. Like, let's say exactly the scenario you had. You did a select for update in one session, and then you inside a transaction, and then you hit the same select for update in another session, right? Like, it could even be an increment or whatever. It doesn't even have to be a select for update. You did some operation in session one, you did the same operation in session two. Can you walk us through how is it that the second session parked and got unblocked as soon as the first session committed? So just a simple case.
Sure, gotcha.
No fancy stuff here. So
yeah, makes sense. So in the first session, when we do the select for update, we are writing a provisional record to a tablet, some tablet corresponding to the key that we're interacting with. Now,
do you mind showing the example, and we'll walk through each step if that's okay with you? We just like ad lib here on the fly. So.
That's a good idea. Okay. Yeah. So in each case, we start the session. On the left, we issue this select for update first. Okay. And when that happens, the tablet that manages ID = 1 in your balances table gets a provisional record that says, hey, this row is held by this transaction. There's a transaction ID corresponding to the session on the left. Now, if at any time after that, the session on the right comes in and says, hey, I want to select from this row, the tablet,
you know that the provisional record exists, so you can't just do it. So you got to do something else. So
exactly. So what we do is we have this in-memory data structure. We call it a wait queue, which essentially will pause this request or sort of hold this operation until the session on the left is either committed or rolled back. And this is all kind of transparent to the client, and what the client sees is just unblocking when it is safe to proceed. But yeah, behind the scenes, we're detecting this provisional record and holding the operation and releasing that operation only once we know that the transaction on the left has resolved.
Got it. Got it. Okay. And so once the transaction's resolved, something kind of notifies it in memory, and that thing gets unlocked. The next guy in the queue gets unlocked, and that thing is able to now go ahead and proceed. And I'm guessing the queue is ordered by time, right? Like in the order in which things come in over time.
Yeah, so that's actually a great question. It is, in theory, ordered by time. There's some nuance because we're a distributed database and we might have failover. And in that case, we can't guarantee ordering. So, it is best effort ordered in a fair manner, but, we can't assume that. But yeah, and that's sort of a small point where we diverge from Postgres, and I'll get to another one later, but in general, we're trying to be as close to Postgres compatible as possible. And I think this really brings us very close to that. And we miss some of the minor details.
And what happens if the transaction on the left here just like dies abruptly? It doesn't issue a commit or a rollback, it just dies. The client dies or something dies.
Yeah, it works just the same way. So the in-memory structure that is holding this operation on the right will be signaled that this transaction on the left has died, and it will release this operation to proceed.
Got it. And who detects once the transaction, like let's say the client or the application that was driving the left side actually died and the client connection got terminated? So does Postgres automatically detect this, and does Postgres do it and we do it the same way Postgres does? Is that the way it works?
Yeah, exactly. So the client, the Postgres connection is a client to the tablet server and is constantly heartbeating, sort of like a keep alive type mechanism. Yep. And if that heartbeat doesn't get to the transaction coordinator, the transaction is considered aborted.
Got it. So if the Postgres client dies, then the node to which it was connected on the Yugabyte cluster, which would have become the transaction coordinator, would decide to would detect that transaction is dead, and therefore would go ahead and abort it, and which would then cause the notification, the whole chain for the next guy to proceed. Okay, got it. That's that gives a clear idea. Okay, so now let's go to the interesting topic of a deadlock, right? Like I guess this is the one where like let's say the transaction on the left tried to select for update Alice and then wants to select for update Bob, and the transaction on the right wants to do the opposite. It wants to select for update Bob and then wants to select for update Alice. So the opposite order. And you could end up in a scenario where the first guy, each guy gets one lock. So the first one locks the Alice row, the second one locks the Bob row, and they're each waiting on each other. And they're probably never going to finish because each one's waiting on the other, right? So how do we deal with this scenario? And I think what's really complicated in the YugabyteDB case compared to the Postgres case is these can be on different nodes, right? They're not on the same node. So how do we, and, like, I guess that's just a simple summary from my side on what like deadlock detection would do. But I mean, I don't know if there's a more nuanced detail in there, Rob, feel free to add, but how would we do it?
Yeah. So I have some visual aids. Let me change what I'm sharing here. Is that sharing the right thing?
Yes, you are.
Okay, great.
See the slide deck, yeah, which I.
Okay, awesome. Yeah, I just want to shout out briefly. Our deadlock detection algorithm is inspired by this paper, and we'll talk a little bit more about the details of our approach in a moment. But it's worth noting that this is what's called an edge chasing algorithm, as opposed to what in the literature is referred to as a path pushing algorithm. Essentially, you can imagine one is we are traversing a graph with probes, and the other is we are pushing our knowledge of a graph down the graph. There are many algorithms to deal with this, but this is sort of the one that was easiest to reason about and has withstood the test of time. And no peer papers describing why it's actually wrong. So it works. And let's talk about what happens. So imagine we have this scenario, 3 tablets, where in tablet 1 we have T1 waiting on T2. Tablet 2 we have T2, and sorry, T1 is a transaction, T2 is a transaction. Tablet 2 we have T2 waiting on T3. Tablet 3 we have T3 waiting on T1. And so obviously from a bird's eye view, we can see there's a cycle between these 3, but we have this information distributed. Yeah. So what we do is every tablet sends this information, say tablet 1 sees T1 is waiting on T2, sends this information to transaction 1's coordinator. So every transaction is coordinated by a specific node. And all of the tablets do this for all of the waiting transactions they're aware of. And eventually the coordinators, in this case, we have 2 coordinators, have a partial view of the what we'll call wait for graph, where T1 is waiting on T2, that's known by coordinator 1, and T2, T3, T3, T1, that's known by coordinator 2. So now, just looking from the perspective of transaction 1, coordinator 1 will drive what's called a probe from transaction 1 down through the wait for graph. So coordinator 1 sees transaction 1's waiting on transaction 2 and knows that transaction 2 is managed by coordinator 2, sends a probe with a unique ID to coordinator 2. And then coordinator 2 sees, okay, I know T2 is waiting on T3, and I also know T3 is waiting on T1. So now I can send back to coordinator 1, hey, for this probe ID, I have T3 waiting on T1. And coordinator 1 knows all of the probe IDs that it's sent and knows which waiting transaction originated that probe, and recognizes, oh, that probe ID was originated by T1, so this is a deadlock. Essentially, we can claim now that their T1 exists within a cycle. And so we declare deadlock, and we begin the process of resolving that deadlock from there.
Got it. And so this is called the edge traversal, right? Or edge something.
Edge chasing, yeah.
Edge chasing, yeah. The other kind of chasing, yeah. Got it. Okay. So yeah, I almost hate to. I'm curious, but afraid to ask what the other option would look like, path pushing. So let's not do it, or maybe.
Well, I can just say very briefly, it would be a situation where coordinator 1 is pushing the path T1 to T2. Coordinator 2 would, add what it knows and push T1, T2, T3 all the way back to coordinator 1 until one of them can see the whole path as a cycle.
Got it. Okay, got it. Okay, and in this case, I'm curious about a different point, which is it says T1 is waiting on T2, right? Though in reality, because of the queuing system, T1 could be waiting on multiple transactions, right? Because there could be, say, 3 transactions ahead of it. So yes. How does it pick? Does it pick all of them? Does it pick the one that's currently running? What does it do?
All of them. Yep. So for any, yep. If there are 3 transactions that have a shared lock on a row, and a 4th transaction wants an exclusive lock, we'll send, the 4th transaction is waiting on all 3 to its coordinator.
Got it. Okay, and so the next thing that comes to mind is, and of course, thank God it's post-coffee hour, so I can actually process this stuff. But the next thing that comes to mind is, how often does this happen? Like, let's say our transaction, the one on the left was T1, right, and is waiting on, or the one on the right, was T1 and is waiting on another transaction. At what point would it send that request would the request go from coordinator 1 to 2, or at what point does all of this happen?
Yeah, so great question. And some of this is subject to, tuning as our database evolves, and will change over time. But the way it will work most immediately is that the coordinator will get fairly real-time updates from the tablet about which transactions are waiting.
Yeah.
And each coordinator will ensure that a probe is initiated from each of its waiting transactions that it is aware of every second. So it's a sort of configurable fixed interval for each transaction.
Got it.
And yeah, I could go into more about that, but if you have more questions, we can get to those. Yeah.
Got it. And this happens on like this just happens on a clock, or is it triggered by an incoming like a statement inside a transaction?
Right. So it happens on a clock essentially. So a transaction will come in and will get picked up in the next sort of 1 second interval that gets triggered. Not from when it gets in, but there's just regular intervals along which it'll get triggered.
Got it. Got it. Awesome. And how does this differ from Postgres? I mean, even at a high level, I'm just curious.
Yeah, so great question. One key difference is that in Postgres, deadlock detection isn't triggered until a transaction has been waiting for 1 second, and that's a configurable thing in Postgres, by the way.
I guess that's how the 1 second comes in. I was curious too. Okay, got it. Okay.
Yeah. So our semantics are slightly different, but pretty close. And the other thing is we, for simplicity, trigger deadlock detection on kind of a regular interval, whereas Postgres doesn't have to do that. Postgres has more guarantees about, if this transaction does deadlock detection and doesn't detect anything, then the next transaction that is potentially involved can trigger deadlock detection, but we don't need to re-trigger constantly. And so eventually we want to make stronger claims about some properties that we can take advantage of. So we can, for example, maybe trigger deadlock detection only twice or some bounded number of times for performance. But for now, we have this sort of easy to reason about approach.
Got it. Yeah, I think, this is more fundamental to the distributed nature, right? Okay, so but at a high level, I guess the important thing is no matter how the sausage is made, it's going to look as close as Postgres as possible to Postgres in a distributed environment, right? Like that's really the aim of the approach, right? Okay, so if you're like a number of users, and myself included, the question then would be, okay, so pessimistic locking and optimistic locking, the choices of these or however it works across different like statements at different isolation levels, it just works in Postgres. When would I understand we have pessimistic locking with read committed, but not quite with the other two isolation levels, which are repeatable read and serializable, but this is work in progress, right? So the question would be, when would it all just work?
Yeah, so
or maybe it started with that question, but anyway.
Yeah.
But anyways, yeah.
Right. So to get pessimistic locking working with read committed is sort of a subset of the work, and to get it working with these other two, we need this waiting mechanism, we need this deadlock detection, and we anticipate in the next month or two that'll land in and stabilize, and we want to aim to ship it in 2.15.1 or 2, and expect it in 2.17 as well, for sure. And
fantastic. Yeah. So it'll ship through 2.15.x's, and so definitely by 2.17 should be available. Got it.
Yep.
Fantastic. Now I'm curious, like the way pessimistic locking works is kind of at a tangent with isolation levels, with other features like save points. So all of that would just start to match and mirror Postgres semantics, right?
Yeah, that is exactly the goal.
You know what's funny? Like I use Postgres I've used it for a variety of things. Obviously now, as a part of YugabyteDB, I learn more and more Postgres every day. But sometimes when asked some of these really detailed questions about how Postgres works, I realize I don't even know how it really works in many cases. And sometimes that just makes me think I just want it to work like Postgres because I don't really want to figure out the differences in these complex things. So it's great that, it's great we're taking this approach to just make it the simplest thing that, people can think about. And those that really care about the details can go into the nuances, right?
Yeah. The Postgres docs are great, by the way. And if you ever make it through all of them, then my hat's off to you.
That's true. Yeah, that's true. Awesome. Fantastic. Anything else that you wanted to add? Anything else that's interesting about the feature?
Nothing specific. I mean, it was really, really fun to work on, and I hope to write more about it. And for anyone curious, definitely check out that paper. And, you know, it's a very interesting area. So I hope I can produce more content about it and, yeah, talk more about it in general.
One last question before we let you go. The other one that probably I should have thought of earlier is, are there any plans to expose this like Postgres would do in a PG locks type table? Is there a way I can have visibility on all this stuff?
Yes, that's a good question. So I can't say that it will match the 217 timeline, but we are planning to expose exactly the PG locks functionality. So you can use PG locks and see what all resources are being held, and it should work mostly like Postgres. Obviously, the schema of what you see will have to be a little different because some of that is very Postgres specific. But yeah, the intention and the plan is very much to add that.
Fantastic. There's one question from Kurt, which is there a facility? It's probably a little unrelated, but still a very interesting question, which is, do we have a facility for querying historical data, select as of a timestamp in YugabyteDB? And I believe we do, right? I think we can add a session variable to do a stale read, and you can actually read at an older timestamp, right? If I'm not wrong.
Yeah, that's right. And I think that allows you also to read at follower replicas in some cases.
Yep. So there you go, Kurt. Yeah. Okay. Type it out for Kurt also. Yeah. All right. Other questions, folks? I think that brings us to time, basically, or a minute over, actually. But thank you, everybody, for tuning in this week. Please join our Slack channel, yugabyte.com/Slack. I think Alexa just dropped the link in the LinkedIn chat as well on the comments. So join us there. Feel free to ask us more questions. Thanks a lot, Rob. This was fantastic. I learned a few things, very interesting and ripe to dive deeper. Yeah, Kurt says huge thanks. And thanks, Kurt, for tuning in. And otherwise, see you guys next week, same time, same place. Thank you. Bye.
Thanks, everyone.